Hi, this is Sholey Physics, APC Mechanics Exam Review number 4. We're looking at impulse momentum and conservation of momentum in this session. So we start with impulse, and again, this idea of impulse and momentum is a stem off from Newton's laws of motion. This is a tool, this is a time-based tool. How does force and time work together to change quantities of velocity and also mass in some applications, or when mass changes. And we start out with Newton's second law, net force equals ma, and just substitute in there that average acceleration during a time when an object is changing its velocity is just that change velocity over time. We plug that value in for a, and we get m delta v over delta t. Bring the delta t over the net force, and we get this quantity net force times time. This is what's called impulse. What's left over on the right hand side is mass times change in velocity, and this is what gets coined as a change in momentum, where P is momentum and the quantity momentum is mass times velocity. So I can probably ask anyone this question and they'll get it right. If you have a large truck and a small car going on the highway side by side, which one has more momentum? The one with more mass. If I've got two identical vehicles driven by identical twins, one vehicle is going 60 miles per hour north, the other is going 40 miles per hour north. Which one has more momentum? The faster one. And one more, I've got a massive, huge train, freight train, fully loaded, sitting at the train station, and a little bug buzzing by. Which one has more momentum? Of course, it's the bug, because the momentum of the train is zero. It has zero velocity. So don't get momentum confused with inertia. Inertia is just due to the mass. That's where we get the aspect of inertial mass from, as opposed to its gravitational aspect. So momentum is looking at the inertial property of mass, how well it tends to continue its motion. So you get a little of Newton's first law thrown in here into the background of this discussion. But getting back to impulse, force times time, when a net force is applied to an object over time, it will change the momentum or change the velocity of that object. So we get this impulse equation. How is it used? Oftentimes you might look at a car accelerating or coming to into contact with another car. If so, what is the final velocity? What is the time of impact or the time of acceleration? It could be a large freight train. Get back to the freight train. What if the freight train is accelerating? Does it take a relatively massive force to accelerate a freight train? No, those freight trains can often take upwards of a half hour to get up to speed. That might be on the long side of it, but if you go from 0 to 60 miles per hour in a car over a half an hour of time, that would be an extremely slow acceleration. But for a train, it's very, very normal. It doesn't take a very large force if you've got a lot of time to accelerate to change your momentum by a lot. Or we could look at catching an egg. If you want to successfully catch an egg that's thrown at you, you need to try to extend that time. So if there's a large time for a change in momentum of an egg, that will produce a small force. What you don't want to do is just reach out and grab that egg, because then it's a very small time for the same change in momentum, and that'll apply a large force to that egg and tend to break that shell. So a small time tends to produce a large force. If you look at this in terms of change in momentum over time, you'll get that inverse proportionality between time and force. You know, to successfully catch that egg, you do tend to give and extend that time. Also, what do pads in sports do? Think of the pads in a helmet or pads on a football player's shoulders. When that player comes into contact with another player, or that helmet gets hit, what do the pads do? They extend the time of the impact. That means the force will be lessened. Otherwise, if you take away the pad, it's a very short time of impact that would cause a large force. Because no matter what, if you get hit, in a helmet, there's a moving object that comes to rest. It's going to come to rest in two different ways, possibly a short period of time with a large force, or of course a large period of time causing a small force. There's also this little critter called a mantis shrimp. It's got little boxing fists in the front. The way it can break through solid glass or through the shells of its prey, it will hit super quick, so there's a very small impact time causing a very large force. So those are several applications of conceptual applications of impulse. Now if we look at this impulse in terms of change in momentum over time, so if we bring that time, that delta t, back over with the change in momentum, we get a new definition for force as a rate of change in momentum. So a momentum time graph is just an awesome thing, especially if you have a known mass to an object. You can get pretty much anything out of a momentum time graph that you want. It is similar to a velocity time graph. You can get the force of an object. Of course, with the force and a mass known, you can determine the acceleration of the object. Divide momentum by mass, and you get velocity. So this could be a velocity time graph just as well. Multiply momentum by time, and what do you get? Well, momentum times time is doesn't really make a whole lot of sense. That would be mv times t. But if you just kind of multiply that out, or actually divide out the mass from that, you get a velocity times a time, and that would be an acceleration. What about a velocity divided by a time? You multiply a velocity times a time and you get a displacement. So the area under this graph could be the displacement if you know the mass. The area under this graph so if velocity times a time, you can get a displacement. So finding the area under this graph and dividing by the mass, you get the displacement of the object. So there's a lot you can figure out from that. Just going back a couple sessions, I introduced the graph and how to look at it, how to analyze it. So first, what does the data show? This data shows that momentum is increasing. What does the slope show? The slope would be momentum divided by the time. So the slope of this graph is the force being applied during this time. What does the area under the graph show? Now again, area doesn't show much, momentum times time, but if you do divide up that mass, you would end up with a displacement of the object. So there's a lot you can get from that momentum graph. If there's a curve to the function, you can look at this in terms of instead of a delta p over delta t, you look at it as a dp dt, a derivative of the momentum function with respect to time. So if the momentum function is given 2t squared plus 3, keep in mind you can take the derivative and find the force function out of that, 4t. So you can figure out the force at a function of any time, like at 1 second or 2 seconds. So the force at 1 second would be 4 newtons, force at 2 seconds would be 8 newtons. All right. And so this is just a reminder down here that you can just as well get a velocity time graph out of this momentum time graph. All right, so another kind of graph you might find momentum involved in is a force time graph, because force is a delta p over delta t, so force times time is a change in momentum. So if you do have a force times time and look at the area under that, that is the change in momentum or the impulse. A question might give you a FT graph. It might ask you, what is the impulse between 2 and 4 seconds? So you could find the area in there. You could find it analytically, look in the graph, break this up into 2 pieces of area, a rectangle and a triangle, and add up those 2 areas. Okay, so that'd be the impulse or the change in momentum. course, if you have a starting velocity, you can then find the final velocity with a change in momentum. If it's a function, let's say a force function with respect to time, negative t plus 5, then we can integrate that. The integral of negative t plus 5 is negative t squared over 2 plus 5t. If we look at that from 2 to 4, we would get the same exact momentum, change in momentum as we did by looking at the graph analytically. So those are all the many different ways you can play around with that impulse equation. Now we're going to move on to conservation of momentum. So again, recall that P equals mv, that piece in there. And conservation of momentum comes from Newton's second and third law. And therefore it always works. That's what we're going to see in the end. I'll come back to that. Newton's third law. Let's say we've got one object coming towards another object. They're going to collide. First object has mass m1 and a starting velocity v1. The second object has mass v2 and starting velocity v2, m2 and v2. So what would the Newton's second law say? Well, Newton's second law in terms of impulse would say force 1 times the impact time is equal to m1 v1 minus m2 m1 v1 final minus m1 v1 initial. So that's the change in momentum there, mv1 final minus mv1 initial. What about that second object? Its impulse equation would look the same exact form. Now it may be a different mass, okay, and have different starting and final velocities, but what will be the same? The impact time would be the same. If we look back up at Newton's third law, the force on object 1 is the opposite but equal to the force on object 2. So these forces are going to be equal but opposite as well. So if we apply that now, I'm just going to, just for simplicity's sake as we move along, if F1 equals negative F2, then negative F1 equals positive F2. So that since F1 and F2 are equal but opposite, then if we substitute F1 here and F2 there in terms of change of momentum and time, divide time out on both sides, we end up with F1 from this expression equals m1 v1 final minus m1 v1 initial divided by time. Now that's negative that I'm going to apply there, so there's the negative. And that equals the positive F2, so we're going to plug in F2, m2 v2 final minus m2 v2 initial divided by time. Plug those in, times cancel, and we're left with a negative to distribute here. Okay, a little distribution of that negative sign. M1 V1 final plus M1 V1 equals all that jazz on the other side. Now we're going to do a little bit of algebra here. We're going to, since there's a final condition on this side and a final condition on this side, let's bring all the finals onto the same side and all the initials over on the other side. So we're going to put all the initial conditions on the left and all the final conditions on the right. Okay. So here I'm adding M2 V2 to cancel this part out there, and that adds an M2 V2 on the left. And then I'm going to cancel out this side, this final condition over here. We're going to add M1 V1 on this side, so we have to do the same to both sides. So these two will cancel over here, leaving M1 V1 plus M2 V2 and M1 V1 final plus M2 V2 final. And what is that? That is the law of conservation of momentum right there. That the first momentum plus the second initial momentum of those two objects equals the sum of their final momenta. Or to sum it up, put it in one expression, the sum of the initial momenta of the system equals the sum of the final momenta of the system. That applies to every single interaction. This is a contact force, an interaction between two objects that changes the momentum of those objects. So guess what? This always works. Why? Because they came from Newton's laws of motion, which always work. They never, ever, ever fail. All right, so to sum it up, our initial momentum equals the final momentum. If you ever get a question, let's say something funky like this, there's a bar, there's a log on some ice, and this dude comes up and jumps on the edge of the bar, and the bar starts rotating as that log starts translating. And the question is the momentum conserved? Yes, always. Is the linear motion conserved? Yes. Is the angular momentum conserved? Yes, it is always conserved. If there's a question like, is the kinetic or mechanical energy conserved? Think about that. It may not be, because sometimes, especially in an inelastic kind of collision, there is a change in mechanical energy, a change in kinetic energy. Some of the mechanical energy may convert to heat or friction or internal energy. So energy is not always, total energy is always conserved, but kinetic or mechanical is not. Is momentum always conserved? Yes, 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 always, always, always. Can't stress that enough for the AP exam. It's one of those questions that is like a 5-second question. You read it, you go, oh, I know this, and click. And you either click or you bubble in your answer. But it could be an easy, quick, correct answer or easy, quick, incorrect answer. So that's one of those that you just remember that little factoid. You always know that momentum is conserved because it's based on Newton's laws of motion. So here's an example. Object runs into another object, and after the collision, the two are moving at 2 meters per second with a total mass of 10 kilograms. What is the initial momentum of the system? Like, what, hold on. They only give us the final values. What do I do here? Oh, it's the initial momentum of the system, not the individual parts. So remember that the initial momentum of the system is equal to the final moment of the system. So that would be the total mass times the velocity. Okay, so, and do take a note, momentum does not have its own special unit. It is just the unit of momentum is the product of its parts, mass and velocity. So kilograms meters per second. All right, so here's several examples. Inelastic collisions. Inelastic is when there's a sticking collision. Sometimes you'll hear perfectly inelastic, which means there is no bounce at all. There is some mechanical energy that is I should say some kinetic energy that's lost in this scenario. But the unique thing to an inelastic collision is if objects are moving along and they lock up, then they're going to be moving together at the same velocity in this. So that includes speed and direction after they collide. So what's unique to this scenario? We've got mass A and mass B with an initial velocity each. And afterwards, consider mass A and mass B might have a different final velocity. But with an inelastic collision, the final velocity is the same for both objects. So let's just drop the VA and the VB. Let's just call it VF as the final velocity of both. So you get the initial momentum of each equals the final velocity times the sum of the two masses. Now hopefully that makes sense now, because we had two different masses to begin with, and after they lock up, after there's an inelastic collision, they're a single mass moving together. So that might be a mud ball thrown at a chicken that splatters and moves the chicken. That could be a couple of cars that, let's say a couple of train cars that are moving and they lock up and they engage. It could be a couple of athletes on a field, let's say in football, they get tackled. So two moving objects that are now locked up together and they move forward and fall over and hit the ground. So that's just one scenario for inelastic collisions. I'll take that off if you want to look at it for notes later on. Elastic collisions, there's a bounce. Oftentimes, to simplify these kind of scenarios, the problem will give a final velocity of one of those objects. If that's the case, let's say there's an elastic collision, same thing as before. So instead of a inelastic collision up top, we're going to have an elastic collision where those same two objects bounce now. So same starting conditions as before, but now there's a final velocity given to 1. And it says there's a perfectly elastic collision. So here's something to keep in mind. If for a strange reason, because this usually takes a lot of time to solve, but it is possible to solve this if you don't know the final velocity of one of those objects. So do keep in mind if a situation does specify that a collision is perfectly inelastic, that does indicate that no kinetic energy is lost either. So in this case, momentum is conserved and kinetic energy is conserved. So you might say the 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So you'd have a second equation to work with in addition to this one, if you didn't know the VA final, or V1 final, I should say. This could be A or B, 1 or 2. Pick one, stick with it for that problem. All right, so here, just to back it up a little bit, we have the M1 V1 plus M2 V2 equals M1 V1 final plus M2 V2 final. Again, I'm using the A's and B's here instead of 1's and 2's. So that simplifies quite a bit. You get a negative 30. We're going to add the 15 to the other side. Divide that sum by 4, and you get a final velocity. Now note, negatives are very important. Very easy way to get a 0 on one of these easy to solve questions is to mix up your directions or not take into account. So this positive 5 and a negative 10 would indicate these are moving in opposite directions to begin with. And because of the negative nature of this, it does indicate that VB will be moving in the same direction as VA in the end, moving in the negative direction. And that does come about from this VB being a larger mass. So in the end, the mass of the system will be moving in the direction of that larger mass. But that larger mass is going to lose a lot of speed, while the smaller mass is going to gain some speed in the opposite direction. So just look into those negative signs. Pay close attention to those as you're solving these problems. Let's take an explosion. A and B are together and bam, they explode apart. This could be as simple as a couple of figure skaters starting on the ice and they push apart and they start to drift apart. That's a very non-violent explosion. Or it could be a rocket that's flying up and it bursts into a couple of pieces. So consider this as the opposite of an inelastic collision. In an inelastic collision, you got two objects coming together to make one, and they might be moving afterwards. Here we have a couple objects that might be moving that split apart into two. So it's the opposite. So consider starting with the momentum of both objects together, mass A plus mass B, moving with a single initial velocity. Just to compare that with the inelastic collision, we had a mass A plus mass B times V final at the end equals their individual initial momenta. But here in this case with an explosion, you got the two objects together to begin with and they split apart into two individual momenta. So this could be an object that explodes. One object has a mass of 2, the other piece of the explosion is mass of 4. But beforehand, they're traveling together for a total mass of 6. And so 6 kilograms times 5 meters per second would be 30 kilograms meters per second of momentum to begin with. Now that 2 kilogram piece of mass is found to be moving at negative 10 meters per second after the explosion. So what about that second one? And we'd have 50 divided by 4, which is 12.5. So if this was a left and right kind of scenario, this negative would indicate that the piece A is moving to the left at 10 meters per second. But we get a positive 12.5, so therefore piece B is moving to the right at 12.5. Okay, so excuse me, that would be that would have to be 2.5. I might be a little off here. No, 12.5. There we go. 12.5. Okay. All right. That would just be from the given information. All right, finally we get to two-dimensional elastic collisions. Now I like these, even though they seem a little bit more involved, they're generally easier to solve. Easier to solve than elastic collisions, especially if we're not given a final velocity. Because what you need with two unknowns, if we didn't know the final velocity of part A, then we would have one equation with two unknowns, and we'd have to grab the conservation of kinetic energy to work with that. But with 2 dimensions, you can get 2 directions of motion, and both of those final velocities relate to those 2 directions of motion. So out of this, we get 2 equations with 2 unknowns. So here's a scenario. Mass A is 2 kilograms, mass B is 4. Mass B is at rest to begin with. All right, initial velocity of B is 0. The initial velocity of A is 5. It's moving in the x direction. It's going to collide. And we do need to know a little bit of information here. Piece A moves off at 50 degrees from that initial starting direction, and piece B moves off at 40 degrees. This often happens in pool when you have objects of equal mass and they collide. One collides with another that was at rest. They're going to move off at exactly an angle of 90 degrees from one another. So here we get 50 and 40 is 90. It may not happen with 2 masses of different mass values. But what we'll look at here is divide out or separate the x direction momenta from the y direction momenta. So let's start with the x direction up here. This object A has a mass of 2 and it's moving to the right with a velocity of 5. So its initial momentum is 10 kilograms meters per second. After the collision, its x momentum, x component of its momentum, will be mass of 2 times the A final cosine of 50. It's going to be the cosine component of this momentum vector, or this velocity vector. So we take the cosine component of that velocity, that's the velocity in the x direction. Now we're going to add to that, after the collision, mass B is going to be moving now. It has a mass of 4, moving with a velocity of VBF cosine 40 in the x direction. So this is a component. This is VBX final. This is VAX final. So we're multiplying those masses by the final velocities in the x direction. So if you look at this expression, you're kind of stuck there. We've got 2 unknowns, one there and one there. So when you get stuck, don't stop. Let's go on to the y direction. Does the object A have any momentum to begin with in the y direction? No. So there's 0 momentum in the system in the y direction. Object B is stopped and object A is only moving in the x direction. So there's 0 y direction momentum. After the collision, the 2 kilogram mass is going to be moving upward with a velocity of, or speed of, VA final sine 50. So you see there's VA final over here and a VA final over in this expression as well. We're building a system of equations, 2 equations with 2 unknowns. And the sine component, the opposite component to that 50-degree angle, is right here. So we're finding that y component for mass A. And now mass B is moving with a downward momentum, so we should indicate that momentum in the y direction for mass B, there's 4 is mass B, is in the negative direction with a magnitude of VB sine 40. Now if I solve one of these expressions, we can solve this by substitution, solve this for VAF. VAF would be equal to, if we bring 4 VBF sine 40 to the other side, divide by 2 sine 50, we'd end up with 4 divided by 2 is 2, and a sine 50 underneath. You could plug that in right up here, and then solve for VB, that would come first, and plug that back in over here to solve for VA, and we get those 2 values of speed. So those were momentum, impulse, conservation momentum, and several examples. I hope that helps you and gets you ready for that AP exam. Thanks for watching.